So good.
I can't imagine.
Yes, whiskey and sausages would be. What's the word? What's the opposite of halal? Haram. Super haram. Whiskey and sausages. Oh no. It's very. I don't think you can make it much worse, can you? Like.
I mean, it depends on what sausage it is.
Pork sausages, of course. Yeah. Yeah. I've never. Yeah. Yeah. The sausages here are only pork sausages. That's all.
I eat chicken sausage.
Just like how the ham is always pork, right?
Huh?
Ham is always pork as well.
Yes. Yeah.
Like our country, we have pork ham, we have turkey ham, and shit.
Do you? Turkey ham? Weird. Okay. Huh? Really? Okay. Now we love pork here.
Yes. Last time I go to McDonald's and
Yes.
I want fried chicken hamburger and they give me chicken sandwich.
That's all they have here.
No.
Yeah.
No, I thought tell you. I said I want this one and they give me chicken sandwich. And last time I thought I told them I want something. I read the hamburger's name and they give me piece of chicken. 3 times. I never trusted McDonald's. I never go there.
You should go to Chinese worker.
Yeah.
And explain what you want.
Well, I read the name. I pointed and said I want this meal.
Yeah.
And they give me piece of chicken. What?
Oh dear. Now remember, in McDonald's the meals have a number, so you can say the number.
Next time.
Next time.
But not that McDonald's. I never trusted.
Try a different McDonald's.
Yes.
Which one was this? O'Connell Street?
City Center. Do you know opposite of 610?
Yeah, O'Connell Street.
Yes, that one.
Yeah.
Never go there.
Okay, I'll be careful when I go there.
Yes.
Right,
Perfect.
Latent Heat next. You got this? Yeah. Okay. Okay, so imagine you have a block of ice and it's slowly being heated. That is, there's a fixed amount of heat going in every second maybe.
Ice maybe.
Yes. Thank you for noticing my reference. For example, 4,200 of joules of heat is given to the block of ice per second. So the power is 4.2 kilowatts. Anyways, the temperature of the ice will increase, of course. Right? I mean, if you put heat under the ice will get warmer, naturally.
And it's gone.
Huh?
And it's gone.
And then it's gone, yes. So let's have a look at the temperature against the energy. So what you notice, look here. Here the ice is minus 100. Then as you put more energy in, what happens to the temperature? It increases. But look here, the temperature is 0 and it doesn't get warmer. But then a little later it starts to get warmer again. And then likewise here, when the temperature is 100, it doesn't get warmer. Even though you're giving it more energy, the temperature stays the same. And then later it will start to get warmer again. So why does the temperature not change here and here, even though you're putting in energy, kilojoules?
Because the energy is used to.
Yes.
The energy is used to overcome the bond.
Yeah, keep it simple now. You're right though. Yeah, as you said also, melting. So what's happening is the energy is not going into making it warmer. Instead, the energy is changing it from solid to liquid. And then here, liquid to gas. So this, hang on. This is called latent heat. This is the energy you need to change the state, solid, liquid, gas. The latent heat is the energy to change a unit mass, to change its state to a different state. without changing its temperature. Wait, before you write it down, wait. I put the last part in red because most students forget to write that in the exam. They just write this much. The latent heat is the energy required for a unit mass to change its state but not change its temperature. And that's really important. Okay. Okay, you got this? Yeah.
Draw the picture, the graph.
Oh yeah, the graph would be a good idea to draw. In fact, sometimes in the exam they ask you to draw this graph. So if you can draw the graph too, please. Now, in the exam, they don't care about having the numbers. What they want is the shape. So it goes up. Wait, listen. I need to tell you what they want for the exam, for this graph. They don't care about the numbers except for they want it flat at 0 and flat at 100. Okay? They don't need what? No. Just write energy. Okay, you got this graph? Yep. Right. So there's a little bit of vocabulary for latent heat. The latent heat of fusion, that's when you go for melting. Vaporization, that's when it's for boiling. You know these words, don't you? Melting and boiling. And then, yeah, actually that's the only two you need. So when it's liquid to gas, which one is that? Vaporization. And then if it's, for example, liquid to solid, that one is fusion. Okay. So can you... Liquid to solid is fusion. Now, sorry, to be clear, is the direction doesn't matter, like solid to liquid or liquid to solid, it's fusion for both.
And for vaporization.
First vaporization as well.
So from steam to liquid.
Yeah, it's the same term because it's the same number. Yeah, when you have a liquid like coffee and you freeze it to make it a solid, that's called fusion. See this word here? Fusion. Fusion is solid to liquid or liquid to solid. And vaporization is liquid to gas or gas to liquid. Okay, continue. Right. So we have a formula here. The energy you need to change m kilograms, but not to change its temperature, just to change its state. The formula is a very simple mass multiplied by latent heat. That's the energy, I'm sorry, let's say delta Q. That's the energy you need to change m kilograms its state. So for example, solid ice to liquid water, if it was 2 kilograms, then you need 2L, whatever L is. It's different for each material, like heat capacity. By the way, what's the units for L? I didn't say it actually, but I think it should be clear. What's the units for L?
Joule per kilogram per degree. Joule per kilogram.
Hang on, one at a time. Your answer?
Joule per degree.
Nope, almost.
Joule per kilogram. Right?
Right. Joule per kilogram. Can you write that down? Actually, the unit is joule per kilogram.
Which two?
For L. Yeah? Mass. Simple mass. Yep. Now, let's have a look. Oh, because.
Yeah, listen, I'm speaking.
Okay. You have it? So you don't listen to me speak. Why so hungry this morning? Yogurt, hot dog.
Too heavy.
Oh, I see. Need a lot of energy.
Yeah.
Need lots of kinetic energy. Yes. Yep.
I don't want to bring my laptop.
Do you need your laptop today?
Yeah.
For what?
Work on no.
Presentation? Is that today?
No.
Practice.
I thought the practice was tomorrow.
That's for 3 days.
Yeah.
Oh.
Yesterday as well.
Ah. Okay. Continue now, Amanda?
Yes.
Okay. Right, so water will freeze at 0. Water will boil at 100, but you know this already. Now, this is the latent heat of fusion for water. So this is if you want to change your liquid to solid for water. You need 334 kilojoules per kilogram. Okay? And you might need, well, you will need that number for some of the questions. The latent heat of vaporization for water is 2,265 kilojoules per kilogram. Yeah? Yeah? Okay. Now, please note that water could be a liquid at 100. In fact, it is a liquid at 100 and will stay a liquid until it gets enough energy to become steam. Liquid. Yeah, liquid, like this. Don't do that, don't do that. Right, likewise, water could be a liquid at 0 until it loses enough energy to become ice. You don't need to write that down. What I want you to understand is just because it's 100 Celsius doesn't mean it's steam. It can be a liquid at 100 until it gets enough energy to become steam. Steam comes out.
Oh.
Yeah. You understand now or not? Yes. Yes. So it could be a liquid at 100 and not a steam at 100. Oh no, you're not writing all of this, are you? No, you are. You don't need to if you understand this part. Continue. I like that you think everything I say is important. It's nice.
Everything is okay, yeah.
But, yeah, okay. Right, continue. Okay, so, oh no, I'll just wait. I'll wait. No, I can continue?
Yes.
Are you sure?
Yes.
Alright. So, don't write this part down. This is imagination time. Imagination. Okay? So imagine the ice is at -20 and I put it on a heater. Or a microwave. Here I put it in the microwave. You know, you all have a microwave at home. Right, so let's imagine what happens. First, it will be ice at -20. What will happen next? Oh, Grace, don't write this down. It's imagination time.
No, I'm imagining the last slide.
Can I continue?
Yes.
Are you listening?
Yes.
Do you need to write this one down?
This one.
Oh.
Yes. No, I am imagining.
Okay, fine. Right, so first it's at -20. What happens next? If it's in the microwave, just turn it around. Yeah. Will it be solid or liquid? Solid first. First it'll start to warm up to 0. It will be a solid at 0 for some time. and then it melts. Then what happens?
Liquid.
Then it will become liquid. Then what will happen?
Yeah, it increases to 100 degrees.
The water will be 0 at first, but then it will warm up to 100. What will it be at 100?
Your water.
It's still a liquid. It will remain a liquid at 100 for some time until it boils. The water is now steam at 100 at first. The steam will start to warm up. Okay?
So until what temperature can the steam go?
I don't know, because usually if it becomes steam, it will just come out the back of the microwave. And then it stops heating up. Okay. So I don't need you to write that down. It's just for imagination. You all have imagination. Good. Good. Right, next. Right, so look at this. Disgusting. That should be on the same line. 100C. Disgusting. Right. Please write this one down. No, I need to fix it. It looks so disgusting. Okay, I'll fix it later. So, write this one down. Our first example.
A kg is
1 kg, yeah. I know, I said ugly. Okay. You got this? I can do it. Okay. So, example number 1. What is it at the start?
Ice.
It's ice, and its temperature? 0. And it's 1 kilogram, to make it easy. 0. Then, what happens? It becomes liquid at 0 also. Then what happens?
Liquid goes to 100.
Then it becomes liquid at 100. Then what happens?
Steam at 100.
Then it becomes steam. Temperature. Yeah. And then it becomes 100 steam. So here is delta Q, here is delta Q, and here is delta Q. But you need a different formula each time. In this first one, do we need ml or mc delta theta?
No.
Which?
Both.
Yeah, for the first one you need which? For this one, step 1,
Latent
step
heat.
2, step 3. You need ml because it's going from a solid to a liquid, but the temperature is not changing. What do you need for this step 2?
MC theta.
Yeah, here you need mc delta theta. The temperature is changing. And then for the last one, what do you need? ml. Now in this example, not too bad because the total will be ml plus mc delta theta plus ml. But please be careful. The L here and the L here are different. This is the L for fusion. I'll write an F here. And this L at the end, vaporization. Now, this example is nice because what's the N? It's just 1. So this will be L, F, and what's the C? It's 4181, and the delta theta 100, plus LV. Now what is LF? Latent heat diffusion. What did I say it was?
Ah.
334 kilo?
Yes.
Kilo. Plus 418100. And then vaporization? 2265 kilo. So in total, I gave that to you earlier. Do you see it? Yeah? So that's nearly 1 megajoule. That's a lot. So if you have 1 liter roughly of ice and you want to change this into steam, you need nearly a megajoule of energy. It's a lot. It's a lot of energy to change ice to steam. Yes? Cold? Huh? Sleepy. But you have a big Americano.
I want to sleep after. I don't know why.
That's very strange. Yes?
When you talk to your wife,
Yes?
did you change your accent?
No. Working here changes it slightly. International students. Okay, we got this? Yes? Continue? Okay. You sleepy as well, Amanda? Okay. Let me see how many more we've got. I think we've got a few. 1, 2, 3 more examples. Okay, write this one down. Okay. Got this? Yes? Okay, let's have a look at it. So you have your cup. How much water is in it?
10.
No, water.
200 grams.
So 0.2 kilograms. And then how much ice is in it?
10 grams.
10 grams. 0.01 kilograms. Now, I was a little bit sneaky. I didn't tell you the temperature here. But I did tell you that they're in thermal equilibrium. Do you remember what that means, thermal equilibrium? It means the same temperature. So if the ice and the water are the same temperature, what temperature must that be?
10 degrees.
No.
0 degrees.
Why?
Because ice and water are the same.
Yep. Go on.
Just because water and ice
Yes.
will change to liquid.
Yeah.
So it's melting and so it's zero.
Yeah, okay. Close enough. I'll explain too. So look, imagine that the ice was -1, for example. Could the water be -1? No. Why not? Because then it would be ice. Imagine that the water was +1. Could the ice be +1? No. Because then it wouldn't be ice. So the only temperature that's possible for them to be the same is 0 for the water and 0 for the ice.
We can reach thermal equilibrium if the ice melts, right?
Oh, at the end as well. Yeah. Yeah. So when you put ice into a drink and then you stir it, it should be at 0. Yeah? Okay. So in this example, I want to make this become 10 Celsius. Yes? So, if you look at the water will be mc delta theta, which will be 0.2 times 4181 times, what's the delta theta for the water? 10. Yeah, we know that's becoming 10. Now for the ice, it's a little bit different. Because for the ice, first the ice must become water, and then after it becomes water, it needs to get warmer. Okay, so what is the latent heat of fusion for ice? What did we say? It was 3, what's the number? Latent heat of fusion. 334. 334 kilo. Okay. Plus m c delta theta. So then the total one two oh joules. 121 kilojoules. Yeah, the total means this one for the water plus this one for the ice. Why like this, yeah? So if you picture the ice, first the ice must become a liquid, and then the liquid must become 10. So it goes 0 ice to 0 water, and then 0 water to 10 water. No? It's a bit like here in the last one. The ice is at 0. It becomes water at 0, and then it becomes water at 10. So this one here is ml, and this one here is mc delta theta. There's 2 steps. I don't know if you're happy or unhappy with that.
Change my
Okay, that might help. Yes. Yes. Look at this mess.
I will.
You will clean it later. Yes, okay. Is that okay? Do you see why for the ice there's 2? Because the ice becomes water, and then the water gets warmer. There's 2 steps.
If the shape is changed,
Yes.
you should use ML.
Yes. If the state changes, you should use ml.
If there is the same
Temperature.
temperature.
Yes.
And use MC delta.
Oh, sorry. Yeah, if it changes the state, use ml, and if it changes the temperature, use mc delta theta. Yeah.
Same state, different.
Same state, different temperature. Yes. Irene, stop texting your girlfriend and focus, please. Are you listening?
Yes.
Good. All right. Next example.
Same state different state ml.
Yeah, something like that. Right. Okay, write this one down.
Oh
Hmm?
my
After this, one more. Be strong. Be strong.
No strong, every day is strong.
Yeah, it's good for you. Be strong every day.
And just like when it's too much strong, when you touch it, the gas is go outside.
Yeah, okay.
What did she say?
Hard to describe.
Yeah.
But you can imagine.
Yes, yes, yes. It's okay, I have imagination, I can imagine. Now this type of question, this is what you might get in the exam on this lesson. Yeah, you got that? Okay, so for this one, you have ice and water mixed. So in the picture, you have your water. What's the temperature of the water? 15?
Yes.
And how much water?
0.33.
Kilograms. And then you put in some ice. What's the temperature of the ice? 0. And the mass, you don't know. So I'll call it X kilograms. Then what happens is you mix it all together until you mix it together until the ice melts, and now the temperature is 5 Celsius. Mix and wait. This here, this melted ice. The ice became liquid. The ice melted. You put the ice in and you mix it, and now the ice is gone. Yeah. Okay, so for this we want to find x. So, the water. Does the water gain or lose energy? Loses energy. And the ice, does it gain or lose energy? It gains energy. Yeah? So, what you can say is the energy which was lost from the water, that should equal the energy which was gained by the ice. So that would be MC delta theta, which is 10. Is that part okay? Yeah? Now, the water will lose energy. It will give the energy to the ice to melt the ice. So this is how much energy the water lost. The ice will get energy. First, the ice will become liquid, and then the ice which was 0 becomes water at 5. So this will equal M, which we don't know, L, which we do know, M, which we don't know, 4181, and the delta theta. What's the delta theta for the ice? What's the delta theta for the ice? 5. Okay. What is the latent heat of fusion? It's 334 kilo. So I get the X is 0.0389 kilograms. So the X is 38.9 grams of ice. Yeah, ice becomes liquid, and then the liquid becomes liquid at 5. It's liquid at, yeah. Okay, have you got this? This is the type of question that they like in the exam for this problem. They like this type, where you mix the ice with the water.
But what is the temperature check again, 10 degrees and not 5 degrees for water.
It was 5 degrees at the beginning.
I mean, it was 10 degrees in the beginning.
It was 15 at the beginning.
Yeah, 15.
Yeah.
Oh, so oh, right, the difference, okay.
The difference is 10, yeah. Okay, continue. Yep. Huh? His question was, I think, where did the 10 come from? So the 10 was the 15 becomes 5 for the water. Okay. Last question. Yeah, I know. I know. And English hates you.
Thank you.
Hang on a second. I need to get something to do this, but I'll do it in a second. Whoops. Okay. Got that? Oh my goodness. Yeah? Okay. Continue? Right, so let's have a look at this one. So for this one, a good picture always helps. You have a cup. And the cup is 0.025 kilograms. And in the cup is some water. And how much water do I have? 250, isn't it? And 25. So here is 0.250 kilograms. Now, you don't know, is that right? Yeah, you don't know the temperature. The temperature is X. So this temperature here, that's X Celsius, and this temperature here, it's the same, it's X Celsius. This is water, and this is copper. Okay, so you understand the picture? Yeah. Then what happens is you have a heater, and the power of the heater is, what's the power? 1 kilowatt, 1000 joules per second, 1000 watts. And how long is this heater on for? 2 minutes? 1 minute? 2 minutes. So that's 120 seconds. And then I think I tell you the temperature at the end, do I? After the heater's been on? No? No, yeah, it's 100 because the water boils. So the temperature then becomes 100. Okay? So first thing I'll do is I'll use this to work out how much energy went in. Yeah? That is the temperature at the end. And this is the temperature at the start. So they both become 100 and 100. Right. Power equals work over time, or delta Q over time. So that means delta Q equals power multiplied time. So delta Q would be 120,000 joules. Where did this energy go?
Steam?
Well, not steam. The energy made the water hot and the copper hot.
So go to the table.
Yeah, it goes into the cup. Do I say steam or not? I say to bring the water to boil, but I didn't say it actually becomes steam. But maybe I will change it to make it become steam. Let me change it a bit. Where's me? To boil off the water. So if you want to change my sentence there, boil off the water, in English that means change all the water into steam. Have you heard this before? Boil off? Have any of you probably know this, boil off, do you? No?
The one actually says it.
But you know it?
Yeah, I mean, but I
Yeah.
don't know what context it is.
I made a small change. So if you see here where it says boil, where's boil? It took 2 minutes for the kettle to bring the water to boil. I changed that to, it took 2 minutes to boil off the water. So you can delete, I'll mark it here, for electric kettle to delete. and you can change it to this, to boil off the water. Yeah, you're back to the question now? Yeah. Did you change that around then? Yeah, and Sophie? Yeah. Okay. Water. Right. So this 120,000, it became energy for the copper and the water. So you can say 120,000. First we have MC delta theta for the copper. Then we have MC delta theta for the water. And finally, what will be the last piece? ML, and this is to boil off. Okay, 120,000 equals 0.025. Can you check from the last lesson what the heat capacity of copper is? It's something small like 375 or something? 425? 385, is it? Okay. 385. Now, what's the temperature change for the copper?
100 minus X.
Very good, 100 minus X. The water is 0.25, 4181, and the temperature change for the water? 100 minus X, yeah.
100 minus X.
Because it's X at the start, and it's 100 at the end.
So you want to find the start?
Yeah.
Oh, okay.
And then lastly, plus M 0.25 L. Now what is it again? No, what is it for latent heat of vaporization is something pretty big, isn't it? 2265 kilo. Yeah, so it's 2265000. Alright, just give you a minute to get this. Okay. Continue. Now this equation is pretty simple, isn't it? I mean, what type of equation is this in maths? What's it called? Yeah, true. What type of equation? Quadratic? My goodness, no. It's not quadratic. What is it? Linear, isn't it? You don't need me to solve this. You all got A's in your math test, didn't you?
No.
What are you talking about? I thought you did.
You are a postdoctoral, can you calculate?
Of course I can, but the time.
Computer should have.
That's what I want to do now. Right, so I'll be lazy. Right, so let's type it in. 120,000 equals 0.025 times 385 times 100 minus X plus 0.25 times 4181 times 100 minus X plus 0.25 times 2265000. That's it. So before I solve it, what type of number do you think X should be? Should it be? No, it's temperature, so. What temperature? What do you think X was at the start? Should it be more or less than 100?
Less.
Okay, good. Should it be much less or a lot less? What do you think?
Much less or a lot less?
Much and lot.
Sorry, bad English. Should it be a little less or a lot less than 100? I think it's going to be a little less than 100 because here, this energy is not so much. Now, if you remember, to make the ice become steam, how much energy did you need? 1 megajoule. So I feel like I should get an answer like 90. Let's see what I get. No, so bad. So bad. I must have typed something wrong. Very bad, very bad. Let me check. Is this right? 120,000 equals 0.025. Okay. That's okay. Plus 0.252265. Is that right?
Yeah.
No, it can't be. No, it can't be.
Maybe it's the first one.
Oh, do you know what? I know, hang on, I know what the problem is. I have too much water, I think. I think I have too much water. Or maybe my kettle's not strong enough. If I change this to 10 kilowatts, let's see if that fixes it. So if I just put a 0 here. Oh, okay, minus is good actually. No. Hang on. I'll make it 3 kilowatts.
400. After heating, become 100.
Hang on. I'll fix this. Hang on. 5 kilowatts. The power of the kettle. The kettle's not strong enough. This is the problem. From the kettle, and it goes into the cup. Alright, nearly there. We'll make it 6.
The number become very
Don't confuse on your per teacher. We'll make it 6 kilowatt kettle. No, too much. 5.5. Okay, good. Good answer. Right, so what I'm doing now is we'll change this to 5500. So that just changes this number here. It's now a 5.5 kilowatt kettle. So this number here is now 660000 instead. And that makes X 11 degrees. 11.1 degrees. Much better. Yeah, sorry. I changed in the story the kettle. Where does it say the power of the kettle? Yeah, 5.5 kilowatts. Yeah, so then that's going to change. Yeah, this will be 5,500. So the energy here is now 660000. Yeah. Wait 1 second. Let me fix my question here. It's now a 5.5. Okay, there's the homework. I know. It's not as long as it looks, I promise.
Every time you.
I know, every time I say this. Okay, got this? Yeah? Close it?
Do you have a knife or something?
Do I have what?
Don't.
Oh, it's not that bad, is it?